Okay, so welcome to the next section on the contact that's available in Nastran and Marc. In this section, okay, so this is what we briefly covered in the previous sessions, or will cover. So next slide shows what we have covered. So we've already done the contact algorithms, why it's needed, and so on. The basics of contact in Nastran and Marc, and the contact table with the interactions. In this session and the next one, we'll talk about the two main contact algorithms in Marc and Nastran, namely the node to segment, which is the older method, and the segment to segment, which is the newer method, which solves some issues that the node to segment has, but then there's some specific additional issues. And we'll talk about what changes and so on in the next session for segment to segment then. Okay, so just to recap the last session we spoke about the contact interaction. So just briefly again, the interaction is part of the contact table, and that's where we specify things like the contact tolerance and bias if you want to override them. So these sections, we can project stress-free, we can specify friction, wear, or separation. There's for touching contact and for glued contact. We have some of the similar ones, contact tolerance, bias, and extension, stress-free projection. But then we can also specify shells to carry moments there. We can allow separation or not. We've got breaking glue as options and so on. So in other words, just to recap, the interactions was just part of the contact table. All of the specific settings between specific bodies. Okay. In this section, we look at the node to segment method. And firstly, let's talk about what we mean when we say node to segment. This is just some top view of a pretty simple contact body contact analysis, and it pretty clearly shows a node there touching a face. So when we talk about node to segment, it means the node is going to touch the segment, and a segment is simply either an edge if it's a 2D analysis or a face if it's a 3D analysis. So that node, in this case, by accident, happened to look like it's touching at that node, but it's actually touching that face. Okay, so how does the contact algorithm in Marc work for node to segment? So let's say a node is not in contact first, because there's two cases. The one is a node is already in contact, and it may want to separate. The other one is a node is not in contact, but it should be. So we've already spoke about the distance tolerance and the bias on this section, so you should know what this means by now. Now let's say in an iteration, a node moves from outside there to anywhere inside that contact region. So that region is defined as a combination of your distance tolerance bias. It includes the effects of the thickness of shells. If you include it, smoothing, in other words, the analytical or the spline surfaces. And if you have any offsets for beams or shell elements, all of that is included in this effect. So firstly, the moment it detects it's in there, it will firstly push the node to the surface. So physically move the coordinates. That's simply a normal projection, normal to that face. And the second step is then to add an equation or link this node to the nodes on that face that it's currently touching. So that contact equation for the node to segment method is simply a type of an MPC. Multi-point constraint. If you're not familiar with the term, we'll briefly talk about some examples of MPCs in the next couple of slides. Okay, so the opposite is if a node starts in contact, then it needs to check if a tensile load exists. If there's a tensile load, in other words, a load normal to the surface that want to separate, it should separate as needed. And additionally, there's some friction checks that it needs to do if it is in contact, if it wants to slide and so on. I add a note there because we'll talk about friction later. The exact method may be either a force or a constraint or a stiffness, depending on which friction model we're using. So for the moment, just bear in mind that there will be friction calculations. I'm not going to talk about what that friction calculation looks like at the moment. Okay, so firstly, what's a multi-point constraint? It's simply an equation that links the motion and force distribution between multiple nodes. So the most common one you've probably seen is something like, sorry, just slip there. So that motion of that node in the center And that's if it's a rigid element, that one rigidly defines all of these nodes' motion. The RB3 looks similar, but that will then be the average motion of the others. We'll talk about them a little bit in more detail. But this equation literally links this node to every one of the nodes surrounding it, whether it's the RB2 or the 3. And this equation is solved analytically. That means if you're using, for example, a rigid element, there's no stiffnesses involved in this element. It's perfectly rigid as the mathematical equation would allow. Okay, so if you look at the RB2, this is something, if you're familiar with Nastran, it came from there originally, but it's been in Marc for the last almost 20 years now. So the purpose of the rigid, if I add, forget about contact for the moment, we'll get to contact. So if I add an MPC between this green node and two red nodes, this one is then going to be the independent, or the master, if you want to call it that. And these two nodes are the dependents, meaning their motion and their loads depend on the motion and loads of this one. So if this node moves in that direction, these two will exactly follow by the same amount in that direction. If it wants to move sideways, so let's say towards that one has to move by the same amount, this one also by the same amount. This connection acts as completely rigid in this case. Okay, so that's for the translation, but what happens if I rotate? If this one rotates about the normal to the screen, this node will translate in that direction, this one will translate in this direction, actually on an arc, but the first linear bit is just that motion in that direction. Okay, so that's for an RB2, which is simply a rigid MPC. The second example is the RB3, which is an averaging one. This is actually a useful one to consider because it's much closer to how the contact constraint equation works in Marc. So in this case, it's the opposite. This green one now is the slave or the dependent, meaning its motion depends on those two nodes. So it's simply an averaging one, but it takes into consideration locations and so on. So that means if that node is very close to that one, most of that node's motion will come from this one and only a little bit from the one further away. It also means that if I apply load to this, it will automatically distribute so that the center of that force, well, not center of mass, but the same equivalent for a force, that acts through exactly the same. So the same total force and moment will be transmitted to these nodes. So in this case, this node's motion is defined by the translations only of these two. Or more if there's more than these two nodes, depending on the kind of analysis. So what that means is if that node moves, let's say up, and this one moves down, that node doesn't translate it because it's simply the average of the two. But to that movement up and this movement down causes a change in that angle. So the rotation is calculated as a function of the translations of these two nodes instead of the rotations as well. Just a side note, averaging rotations doesn't really have meaning, so it's a very unsafe way of doing things. Now, this node is the dependent one. By that, it means this node's motion is purely defined by those two. I can do anything there. I can constrain them, apply loads, anything, and the model will work. The dependent one, the center one in this case, I cannot apply a constraint to. I can apply a force to that though. So that force will be redistributed. I cannot constrain it. Yes, I know there's methods to change the order around, but in 99.9% of the cases, probably that'll be the dependent. Now we get to the constraint equation or for contact specifically. Similar to the RB3, this node, for the node to segment, so that's the node and the segment, that motion is defined, or that node is firstly defined as the dependent, so the slave. These are the independents, the masters in other words. But the equation simply says motion normal to this is defined by those two, but no other motion necessarily. The exception is if I have friction and a specific friction models, I can also add additional equations in this direction. So what that means is this node's motion is completely defined by that effectively face, because these nodes are connected to that face. So if this moves up and that moves up, this will stay in that same location in space. It may, depending on the kind of load and friction model, it may slide a bit, but it will stay exactly on that edge. So no normal translation. Okay. So as you can see then, that contact between the two bodies, the node and the segment, is infinitely stiff, which at first glance may sound a bit bad because there's something like a contact stiffness. Yes, well, if I just go back to this, that load will still deform the structure below it and will deform that structure. So that is already taken into consideration in the mesh. If you want to separately calculate some kind of a contact stiffness there, that effect is due to microscopic imperfections and so on, and that motion should be insanely small. So if you really want to, it's possible to model that, but it's a bit more work to do. Okay, so in other words, the contact is infinitely stiff. The material cannot penetrate into the other material. So this is not like if I press an indenter into another material. In this case, it'll do the exactly correct thing, because the nose of the one will deform the mesh of the other. In other words, the indenter will cause that penetration as you expect, but the material isn't diffusing into the other one, because that's what contact penetration would have meant. So the one material kind of diffuses into another, which is not really physical. It's a mathematical equation that's being solved. So because of this, we get both infinite stiffness, which is what we want, but also if we replace this with a stiffness-based method, penetration or a penalty method, Lagrangian multipliers, depending on the method and so on, all of those has some kind of a stiffness involved. And ideally, we want that stiffness to be as high as possible. But the higher you make it, the less likely the model is to converge, or we actually can get to a significant round of errors. So the advantage of using this infinite stiffness equation means we don't have that possible round of error that can occur due to a stiffness-based method. Okay, so that's the good. Unfortunately, there's some bad qualities that come with it as well. So one of the features of an MPC is a degree of freedom of a node can only be dependent once. So not the node itself, a specific degree of freedom can only be dependent once. Because again, if I go back to this slide, if this is an independent, or sorry, the dependent, if these two tell it to move, it has to move exactly how these tell it. But if for whatever reason, so other nodes want to do the same independently of these, the two will conflict and there will be no solution. Okay, so in other words, because a degree of freedom of a node can only be dependent once, that node can also, per definition, only make contact to one segment. There's a minor special case where if it's in the corner of a continuous mesh, which let's say you've got an angle between two meshes, it'll effectively stick in that location. So it's a slightly more complex equation that it needs to set up, but it's a special case that's easily treatable. But anything else, if it, especially if it's touching two separate bodies, is not physically possible using the node to segment method. Okay, so when we get to the next in the series on the segment to segment, we'll get past this. But then, because we now, in that case, have the both of them visible and so on, it'll be easier to explain examples of why this can be an issue and what kind of models and how we actually have to work around this. Okay, so that's the first one. The second one is a bit more subtle, but also a significant pain in this kind of things is any degree of freedom of a node may not depend on itself. Doesn't matter how many multi-point constraint equations we have. Okay, so the complication here is if you use double-sided contact. Now let's just step back a bit. Right at the start, we spoke about single-sided and double-sided. It simply means single-sided means I'm checking one body node against another body's faces. Double-sided means I check body A's nodes against body B's faces. Then I swap around and do the same from body B back to body A. So the nodes of body B back to body A. So that said, if I have such a case and by accident we pick the wrong order and it picks bad nodes or a bad set initially, when it swaps around, we may end up with nodes that should have been in contact, but because of this, Marc doesn't add them because then it would cause the circular dependency. So let's okay, so let's look at 2 examples of the things that can go wrong. So this is not a single mesh. This is a stack of boxes on top of each other, whether it's bricks or I don't care. It's just physically boxes. In other words, at every one of these seemingly corner locations, we've got multiple nodes. Every element has its own set of nodes. So in reality, I know this is going to be stable. There's no complications in terms of loading this. If I apply load and I fix it at the bottom. But in terms of node to segment, if I want to model each of these boxes as a single hex element, it's not going to work. Because if I look at that node for the element bottom right, that node can only make contact to one face. So does it make contact to this face, to that one, to this one? And it depends on which one it by accident picked first. So the same goes, this, the one next to it, that node in the same location can only make contact to one. So if I try and load this, I'll see nodes moving through faces simply because nodes are already in contact. If it was possible, and that's kind of what the segment to segment does, to specify the contact on the faces, there's no issue because that face of this element is touching the face of that one. Now, just bear in mind that in a finite element model, we're transferring loads purely at nodes. If I actually apply a load at a face, it's converted to forces at nodes. But when we solve F is equal to KU, force is stiffness times displacement, that's displacements at nodes. There's no forces at element faces or anything. Everything has to happen at nodes. So again, the algorithm will in the background have to translate between this dual concept of faces and nodes, but that's its problem. Okay, so in this case, node to segment, as you can see, will not work simply because a node will make contact to wrong faces. Things we can do would be to apply some kind of a small chamfer, for example, to allow, let's say, this box to touch this one on the one node, but another node sideways. But that means you have to actually spend a bit more time in meshing. If you mesh finer, it'll also work, but not that great because the nodes on the edge will also always do something slightly weird. The nodes in the inside, at least, will be able to transfer the load as expected. Okay, so this is one of the special cases. Now, to be honest, it's not something we see a lot, but it is something to be aware of at least. The second one is this kind of case. So let's say I first check from the bottom to the top. So the nodes of the bottom to the face of the edges of the top. So I look at node 3, and that node 3 touches that face. Great. The equation is added. Node 3 is linked to node 7 and node 8. So as you can see there, node 3 is linked to 7 and 8. But now if I stop there, I've got a hinge because I'm only making contact in that one location. This node can move down, that one can move up, and nothing happens to this node. So now we try and swap it around. Now we say, okay, let's just check the top node to the bottom. So in other words, I want to see nodes 7 and 8, whether they make contact as well. So the algorithm does that. It says, okay, node 7 is linked to node 4 and 3, that face, and 8 is linked to 3 and 6, that face. At first glance, it sounds okay, but if I add these equations as well, node 3 depends on the motion of 7 and 8, but 7 depends on 4 and 3, meaning 3 depends on 7, which in turn depends on 3. So in other words, that node's motion depends through that back onto itself. So all that Marc will then do is to say, okay, I can't add these because we'll cause circular dependencies, which is impossible to solve mathematically. So then it simply leaves these out. And in that case, obviously, this model won't even run. It'll act as a hinge over there. If in the same case, I swap them around, so my contact from the top to the bottom, I only have this pair because that face is already linked to that face and to this face through this node and that node. So effectively, I don't need to check from there up again because that node's motion is already defined by the face above it. Okay, so yeah. Just a second. Okay, sorry. Someone is marking the office was just by accident on. Okay, so the last thing I want to talk about is the algorithm that's being used for the notice segment, because understanding this makes it a bit easier to understand why in some cases you get lots of iterations and sometimes problems. Okay, so at the start of every single iterations, by default, Marc will check if any new nodes come into contact. If it finds any, it will add those equations, move the nodes to the face, all of that stuff. But then it will also restart an iteration. Whether or not it's converged, it doesn't care, since the contact status has changed. Okay, then at the end of every iteration, it checks again if any nodes came into contact. In other words, whether it needs to start a new iteration. So then it redoes that. But if no new nodes come into contact, it says, okay, let's check if convergence has been met. So we've got some convergence criteria on displacements and residuals and whatever. So if they are met, only then does it check should nodes separate. So it doesn't check every iteration if it should separate. It first converges. So new nodes can come into contact, no nodes can separate until it's converged. So once it's converged and it detects nodes which can separate, it removes those constraint equations, and then it resets the iteration count to 1, and then it restarts the iteration process. Okay, so no result is written because the contact status wasn't correct, even if the system or the convergence tolerance and force and displacement may have been met. So if no nodes should separate, in other words, the tensile force is either insanely small or non-existent, then complete the increment. Complete the increment means write the results, mark it as a valid set of data, and continue to the next step where you increase the load or whatever the case would be, and restart the iteration set. Okay, so the complication here is, and this is something you've probably seen quite a few times, you start with a model in contact, and then as you load it, it has to lift up, separate in a pretty large area, and only a small region may stay in contact. And in that case, every time it needs to converge before it releases the next set of nodes, which is intention. And it keeps on doing that until it's converged. So in that case, what you typically see is that your first increment takes a lot of time and effort to sort out the contact status, and then after that, it tends to go a lot faster. And the reason is, again, because of this, it separates only after it's converged. Okay, so the reason the convergence or the separation is only allowed after convergence has been made is simply this allows for a much more robust algorithm. If it separates too soon, Marc will start to chatter severely. Nodes come into contact and separate over and over, and it may actually cause divergence. So while it can, in some cases, significantly slow down the run, at least it's more robust and it should get to an answer. Okay, now there is a workaround that they've added relatively recently, I think 21 Marc, maybe Marc 2020. On the job, there's an option to change the checking for the separation from to accelerated. So it's if you go to job, contact control, advanced contact, there's an option there on the right-hand side that says check, default, I think, and the other one is accelerated. What this does is it doesn't completely ignore the convergence. It simply says, even if it's not converged, but the tolerances are at least reasonable, it's usually about 10% error, it then checks for separation. So this will allow the model to much sooner start the iteration process with the new separated nodes, but still at least start in a reasonably converged state. Okay, so this usually reduces the number of iterations required for convergence. Sorry, I see a typo there. We're not talking an order of magnitude necessarily. It's sometimes 20 or 30% faster that it gets, especially to that first one. But usually throughout the run, we see the same kind of behavior. Okay, so that's the only thing we can at least add that should improve the runtime of the node to segment method. There are a couple of other options in the same location, which I on purpose didn't mention. There's suppressed chattering and a couple of other things. Please don't use them. They're useful only to initially debug a model just to get to a fast result, but the contact isn't sorted out at the end of those increments. So your answer is going to be wrong, and you have no idea whether it's marginally wrong or really badly wrong. Okay, so this one doesn't do this. It simply separates slightly sooner. Okay, so the node to segment method is older than the segment to segment method. The first time I've seen and used Marc more than 20 years ago, node to segment already existed. Segment to segment came a lot later. It's really robust. They've tweaked this quite well. So it's much more likely to converge than the segment to segment. But there are, as we've shown, specific complications by using this. So we tend to get a better representation of the stiffness for certain models. So by that I mean, because the segment to segment is again some kind of a stiffness based method, if that contact stiffness is for whatever reason lower than the stiffness of the elements surrounding it, we're going to get the wrong stiffness for the total structure. Okay, but that said, we need a bit more thought in setting up a node to segment model because the direction of checking is important. Quite a few of the other parameters that we've discussed in the past sections has to do specifically with the node to segment method. So a lot of that is easier to do when we get to the segment to segment. Okay, so just briefly, in the previous sections, we spoke about contact algorithms, the basics of contact, the contact table. In this, we introduced and spoke about and explained the algorithm and method behind the node to segment method. In the next one, we'll look at the segment to segment and also some comparisons between the two, and when the segment to segment method may be okay, when it's good, and when it's exceptionally good. There's certain kinds of model where it works exceptionally well compared to node to segment, but the same goes in the reverse as well. Okay, so that concludes the presentation I had in mind. Do you have any other questions?